Hello, today we're going to draw the trigonometric unit circle and derive all of the degree and radian measurements using only the four tools that you see in front of you: a pencil, a precision compass, a watch, and a straight edge. Let's get started. We will do all of this using the basic principles of sacred geometry, which, if I could sum it up in one sentence, would just be drawing circles for fun. Let's start with a small circle. And then we want to create what's called a Vesica Pisces. And all that really amounts to is inscribing a second circle over the first, somewhat vertically. It doesn't really matter. The verticality and horizontal nature of this circle will appear from the image. Okay, so this is what's called a Vesica Pisces. And Pisces is a word that means fish. And it really stems from this central ovular shape here. This is called the Vesica Pisces, this center shape here. So let's just start with that because we really don't have anything else to work with. So if I am just thinking, what do I do now? I need to draw a construction line, a horizontal construction line to continue building my circles. It's not required, but it will be a useful guide to us, and it will help me orient both the camera that's videotaping this and my own continued construction of the unit circle. So I can draw a horizontal line right now by noticing that this point and this point lie directly across from one another, and I take my straight edge and just connect the dots. With these first few circles, it's important to take your time and be precise. And even there, you noticed I needed to turn the paper slightly to make it appear straight. But that reference straight is only relevant to my eyes. So let's continue. We're going to create something called the Germ of Life now. And really, the major rule is to just keep drawing circles. So we're going to draw circles in a clockwise pattern around that vesica in the center and just see what happens. You're setting your compass at the intersection point of the circles. And it's once you do this yourself, it becomes obvious what to do. And there we have it, the germ of life. And the important point now is this little flower petal shape that's emerged right here. I'll just take a moment and highlight it for you. You'll see these little flowers all over what we're about to draw. But many geometric shapes can be derived directly from the flower. And we'll take a look at a couple of those before continuing, just for the sidebar annotation and enjoyment of it. Remember, our goal though is to get to the unit circle and talk about degrees and radians, so I won't spend too much time on this, but notice there are 1, 2, 3, 4, 5, 6 points on the flower. And if I were to connect those points, again, this has nothing to do with the unit circle, but if I were to connect those points, I would form a six-sided shape called a hexagon. Many other shapes can be formed this way. But you see there, I've got a hexagon. Okay. I also have the ability now to draw a perfectly vertical line. So I was able to draw a horizontal line a moment ago, and now I can draw a vertical line. Because I have this point here, and directly below it I've got that center of the flower, or petal, and I've got this point here, and I can make those into a vertical line with my straight edge. And there we go. Reorient again. This is a perfectly 90-degree angle now. So the question is, now what? Well, it's merely to continue drawing circles. So I'll start up here with another circle. And just proceed as before around the perimeter of the germ of life. And I'm going to complete this circumambulation with the compass twice. It just takes a minute. And so with this final circle, I'll have completed the first tour around the germ of life, and now I'll proceed again from this point above. And then I'm just going to travel around in a circular fashion. at this point you will see many flowers begin to take shape. They seem to have an internal pattern structure that will become relevant when we make the unit circle. So it's important to stay precise with your inscriptions and your circles. Part of the majesty of this whole process is just trusting in the circles to let the patterns emerge without too much thought on your part. Makes it easy for a dummy like me, because I don't see the patterns without help. So, and there, I've completed 2 complete rotations around the germ of life. Now, we can, I think, we may need to draw more circles, but I think at this point we can find the main angles of our unit circle. This is putty for a sundial experiment, but I believe those I believe the raw material is there. So we'll start with the 45-degree line since that's the most visually obvious. Just take a look here. I've got this. Well, I guess it all depends on where I'm going to anchor my circle, but I suppose we should anchor it around the center of this dot right here. We could do that. We certainly could. Yeah. I don't know. Let me take a look at it with another tool. This is a cheater tool, but it can help because there's so many circles that I'm not quite sure where to put the marker. Now there's 45 degrees. If I put it there, 45 degrees. Let's see where 30 degrees is clear. 60 degrees is clear. And if I put it here, .60 degrees is not clear. Neither is 45 degrees, 30 degrees, neither that. So I think the best place is to center the unit circle right over the flower of life. Let's do that. Let's just see where that takes us. I see a point here that looks like 45 degrees, so I'll just make a little dot there. And you don't need this tool, okay? But it's just a helper. I'm gonna say you couldn't depend on the tool, but with the sacred geometry, if you see certain correspondences and you happen to have that tool, it can be a bit of a helper. Remember, I'm going through this point here, so I'll need to erase this construction line since my new origin point will actually be here. I guess I might as well draw that. And then we'll use one of these erasers to try to erase a bit of this line. Okay. All right. So through my center point, I can draw my 60-degree angle here. That's 60 degrees. And 45 degrees is just 15 degrees offset from that. And that will pass through here and here. So I'm going down here through the origin and up through here. .45 degrees, and then finally 30 degrees, which is again 15 degrees further offset. And what I'm doing is going through this point here, through the origin, and I'm going to see where that leads me on the other end of the straight edge. So I'd follow that through the origin, and bingo, it passes through this point here. So that's how I know that I'm getting a clean angle. Okay. Okay, and now I'll just do this for these axes here, or sorry, these quadrants rather. And I can kind of, since this is a symmetry, I can start here and say, well, here's one intersection, and then that second intersection was the 60-degree intersection. That's kind of the thought process. So boom, and then right here is where I'm going to put my 60-degree angle, and then one arc over is the 45-degree angle. And then right here down is the 30-degree angle, all in relation to this center point. So we'll draw those in. Line up with your center. Sometimes it helps to put your pencil there, then slide in the straight edge. And we see that we're going to go through the center down to this point right here. So we're going to pass through those 3 points. And there's other points we're passing through, but those are the guide points. And that's 60 degrees from this x-axis and 30 degrees off of the y-axis, or the sine axis, if you will, and we'll get to that. But let's draw the other lines so we have our full complement of angles. So here comes the 45-degree angle. So far, so good. And then finally, the 30-degree angle, which is that point. So we've got our line this point up with the origin. And I see that it passes through this guy down here. So those will be my 3 points for the other 30-degree angle. Okay, so just for visual harmony, I'll draw back in those circles that got kind of erased by my mistake, my drawing that big old line. Okay, with an exception here or there, we've recovered most of the visual harmony of the original circle. So now what? Well, we have, let's go back to our goal. We have 30 degrees, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then 360 or 0. We have all those there. And now it's time to look at a watch. I want to introduce this metaphor quickly and early so you see the interesting relationship here. So before I start writing angles or drawing circles to make the unit circle. Let's just look at this and meditate on this for a moment. I have the watch hand set to the hour hand is at 3 and the minute hand is at midnight. Okay, so that's pointing at 0 degrees or 360 degrees depending on how you look at it. Remember in Trig, we go counterclockwise. There's no reason for this, it's not important, but it's how the trig circle is drawn, so that's how we'll draw it. Now, if I turn the hour completely back in time to where now my hour hand is on 2 o'clock, you're going to see something pretty fascinating. The only important thing is that the little knob here is lined up, and this hour hand is lined up all on this line here. This serves as an axis, and so let me pop the time open here and turn the clock back to 2 o'clock on the dot. Set my watch back down, and you see that the hour hand on 2 o'clock is now it's pointing directly at this angle here, which we know or we'll find is 30 degrees. And now remember, this jumped 30 degrees, then we jump 15, 15, and then again 30. So in order to find if 2 o'clock is this line right here and this line is 30 degrees off of the horizontal axis, let me jump another hour and see where we go. And we're going to see that we're going to skip one of our lines. So if I jump a whole nother hour back at 1 o'clock now, get everything oriented correctly, the hour hand points right through the 60 degree line. So 60 degrees up is the 1 o'clock hour hand now. So we miss this guy here. Who is he? Well, we know that he's 45 degrees. where can we find him on Mr. Clock? Well, most people will intuitively recognize that if all of those were full hour rotations and each hour rotation represented 30 degrees of arc, then perhaps a half hour rotation will represent 15 degrees of arc. And indeed, it does. So 130 represents the 45-degree angle. Okay? So that's enough for the watch. The watch is broken, is really just another unit circle. It is a 12-hour clock face, and the unit circle is a 360-degree clock face. If you'll take the metaphor of the unit circle as a kind of clock. I could, before I get rid of the watch, if I wanted to construct a clock face on paper, I could continue to go up by half hour and find, or rather by hour, and draw in all the missing lines. 15 degrees of arc represents half an hour, and hours are broken into 60-minute segments. So if 15 degrees represents 30 minutes, then 7.5 degrees represents 15 minutes. And we could draw in, and what I'm trying to say here is we could draw in all 12 hours of the day and the 30-minute marks on the clock. And we could erase the 45-degree angles and just have the hours drawn and create 12 lines. It's fairly obvious I would need one more here. And I could draw all of my the 12 hours of the day. But we're not here to draw a clock, we're here to draw a unit circle. So let me just show that geometry is cool before I continue. If I kind of skip along the tops of these circles and go all the way around, another platonic shape will emerge naturally from the drawing. There's no harm in doing this, why not? I just think it's cool. I wish more of school was doing things just because they seem like, hey, this seems like it's a cool thing to do, let's do this. It seems to me that kids in class really love drawing shapes. So my pencilette is wide. Okay. I still need to. It's easier to come at the circle or the shape from the other side, and you can't see the points so well if you do it the other way. A little too close there. Cool. IMHO, it's cool. What have we got? Well, let's count the points. 1, 2, 3, 4, 5, 6. We have another hexagon. How interesting. Let's draw a unit circle. How do we do that? Well, we take the compass and put the pointing end right there in the center, and we put the pencil lead up here. And we're going to create a, if I put the pencil lead on top of the line I made, okay, so not right there on the top of the circle, but where the two lines of the hexagon intersect. If I put it right there, I'll create a circle that goes all the way around this shape. And I won't be cutting off any of it. I'm drawing it real soft at first, and then I'll go over it a few times. And this will be our unit circle. Okay, very cool. If my value criterion for trigonometry is awesomeness, I think that looks pretty cool. To me, it looks more fun than this, but it is the same thing. I hope you see that. It's the same thing, exactly the same thing. And quite frankly, it's more accurate than this, because how do I know how this was created? I could open up PowerPoint and put some lines in there and not really have any mathematical certainty that I'd created all those angles correctly. But if I use my cheater tool, I can verify that I did all of that. There's 60, 45, 30, 0, there's 90. Okay, that was midnight. Then I go over here, and I'm 30 degrees off the 90-degree angle. Whoops. I'm 30 degrees off the 90-degree angle into the second quadrant. Go down. Now I'm 45 degrees off the 90-degree angle, which is, so this 120, 135. Now I'm at 60 degrees off of the vertical axis, or 30 degrees off this horizontal axis. Back to where 2 o'clock was over here. I'm now at 10 o'clock. You know, they tell you when you drive a car, put your hands at 2 and 10 on the steering wheel. Well, that's what we're doing here. Here's 10 o'clock, and here's 2 o'clock. It's the same angle, 30 degrees from 3 o'clock to 2 o'clock, or from 0 to 30 degrees. And then all the way around. If I'm at 180 degrees, I just go up 30. You subtract 30 from 180, you're at 150 degrees. Subtract 15 from that, you're at 135 degrees. Subtract 15 from that, you're at 120 degrees. Subtract 30 from that, you're at 90 degrees. Subtract 30 from that, you're at 60. 15 from that, 45. 15 from that, 30. 30 from that, back to 0. And we could do the same thing on the bottom and continue all the way around the unit circle. So now it's time to label it with the information we kind of knew ahead of time, which were the degrees. So let's start with that, because degrees seem simple, radians seem weird. But I'll explain what radians are, hopefully in a way where that's the pi, 3 pi, 2 pi, pi over 3, pi over 4, all that nonsense. We'll find out that it's not at all hard to come up with those measurements. But let's start here. This is 0 degrees. Okay, it's also 360 degrees. That'll be important in a moment. And we know this is 30 degrees up, so that's 30 degrees. This is 15 degrees more than that, so this is 45 degrees right here. And of course, I'm referring to this angle. This angle. That's a 30-degree angle. That's a 45-degree angle. And this 15 more degrees up is 60-degree angle. 30 degrees up from that is 90 degrees. 30 degrees up from that is 120 degrees. "30 degrees more is 135 degrees. I'm sorry, 15 degrees more is 135 degrees, not 30. 15 degrees beyond that is 150 degrees. And then we go 30 more, and 150 plus 30 is 180 degrees. And I will continue. I'll fill out this whole thing for you. 180 degrees plus 30 degrees is 210 degrees. 210 degrees plus 15 degrees is 225 degrees. 225 plus 15, see, 235, 240, 240 degrees here. Then we add 30 more degrees to get back to what would be 6 o'clock on the watch. 240 plus 30 is 270 degrees, and that's right here. "270 plus 30, that's 300 degrees. "300 degrees plus 15 is 315. 315 plus 15 is 330. And thank heavens math works. 30 more degrees brings us back full circle, pun, to 360 degrees or 0 degrees. Okay, not bad. Not bad at all. We will now add the radian measurements. Dun, dun, dun. Which seems scary, but really aren't. This is where it helps to move from thinking about this as a clock, in my opinion, and thinking about it more like a pizza that's cut into these pieces. Let's start, and let me actually draw this in with a deeper, bold, more bold line. It seems like everybody's favorite angles are 90. Everybody's favorite angle is 90 degrees. We all know about 90 degrees. Now, how many pieces of pizza do these two lines cut the pizza into? Well, it cuts it into 4 pieces, but just this one line, imagine that no lines were there, none. And imagine this, maybe a better a metaphor or analogy here from pizza would be, I don't want to use the word pi because we're going to be talking about pi, the number 3.14. But if we think about this, if I just draw a vertical line, if I just draw a vertical line, I'm cutting the pi in half into 2 pieces. Okay? So this one over here, this radian measure, is pi over 2, but I don't want to write that first. I don't want to write that right now, because that, ladies and gentlemen, is why people get confused, in my opinion. Let me remind you that this unit circle, there are more, as it's said in Hamlet, there are more things in heaven and earth than are dreamt of in your philosophy. There are more lines here than are shown in the unit circle. The unit circle shows 1, 2, 3, 4, 5, 6, and so on. But remember, it only shows a few of the degree measurements. But there are actually 360 degrees in a circle. So there's really 360 of these lines, but it's cumbersome to draw them. Each one of those lines has a radian measurement. Each one of them have a cosine and sine fraction that go with them. But how do we find them? Well, there's a trick that I will show you. Let's go back to 90 degrees. Let's start there. It doesn't matter where we start. But the trick is you take the degree that you have, multiply it by 2, and divide by 360. Let me say that again. Take the degree as a whole number, multiply by 2, and divide by 360. This will work to create the radian for every single angle that you can think of as a whole number. Every single one of them. 90 times 2 divided by 360. 90 times 2 divided by 360. Here's the key. Pi. So let's do this. 90 times 2 is 180. 180 over 360 is 1/2. 180 divided by 360 is 1 over 2, because 180 goes into 360 twice. So 1 over 2 pi. That's another way to write the radian measurement. This is a perfectly valid way to write the radian measurement, but that's not what's in your book. Okay, what's in your book is the reduced fraction. So 1/2 times pi can be written more succinctly. We will all admit it is a better way to write it. And I'll find another place here. Another way to write this is pi over 2. That's exactly the same thing. That's 1/2 times pi, which is the same thing as 90 times 2 over 360 times pi, 180 over 360 times pi. You reduce it down and you get pi over 2. I hope that's clear. Let's just keep doing these angles and we'll see it happen over and over again. It'll become second nature to you. You'll see that not only can you find the radian measurements for all of these angles, but you can find it for any angle between 0 and 360. Let's take 30 degrees as an example. 30 times 2 over 360. Times pi. That's the radian measurement. Let's do it in our heads. We don't need a calculator. 30 times 2 is 60. So 60 over 360 pi. Another way of saying it is 60 pi over 360. But 60 goes into 360, doesn't it? How many times does 60 go into 360? Another way of saying it is, what's 360 divided by 60? Let me ask you another question. What's 36 divided by 6? The answer is 6. And so this becomes 1 over 6 times pi. Well, that's cumbersome. So a cleaner, simpler way to write that, more ergonomic way to write that would just be pi over 6. Is that clear? If that isn't clear, we'll continue. We're going to do this for all of the angles that we see here. So buckle up. If you're easily bored, this may be something you want to fast forward through if you're getting the concept. But let's take 45. 45 times 2 over 360. I'm not even thinking as I'm writing this. Times pi. Well, what is that? 45 times 2 is 90. 90 over 360 pi. Perfectly valid radian measurement. But we can reduce that fraction. 90 goes into 360 in an even number way. Well, how many times does 90 go into 360? Well, I don't know because I'm an idiot. How many times does 9 go into 36 though? I know that one. 9 times 4 is 36. So 90, 9 goes into 36 4 times. 90 goes into 360 4 times. So that's 1 over 4 times pi. Well, a simpler way to write 1 over 4 times pi is pi over 4. Okay? Let's keep going. 60 times 2 over 360. You're saying, hey man, I get it. Let's move a little faster. But while these angles may seem obvious, how about an angle like, I don't know, 31 degrees? Well, what would be the radian measure of 31 degrees? Can you guess yet? Well, I don't need to think, ladies and gentlemen. I just need to say 31 times 2 over 360 times pi. So 31 times 2, what's that? 62 over 360 times pi. Well, I have no idea how to divide 62 into 360. But what I do know is that I can divide both by 2 because they end in a 0. It's an even number. So let's see, 62 divided by 2 is 31. Okay. 360 divided by 2 is 180. So it's 31 pi over 180. That would be the radian measurement for 31 degrees. 31 pi over 180. Anyway, so let's do this one. 60 degrees. 60 times 2 is 120. I forgot to write pi. So 120 pi over 360. Well, how do I reduce that down? 120 goes into 360. Okay. How many times does 120 go into 360? I have no clue. How many times does 12 go into 36? Well, I know that one. 3. 3 times 12 is 36. So 120 goes into 360 3 times. An easier way to write that, so that would be 1 over 3 times pi, but we can just write pi over 3. And we've already done 90. 90 times 2 is 180 over 360. That reduces down to pi over 2. $120. You don't have to think. Everybody freaks out like when they go on this side of the... Everybody's comfortable with this because we've all been working with quadrant 1 our entire lives. You get over here and you go, what do I do? Well, don't think. Just write 120 times 2 over 360 pi. What's 120 times 2? 240. 240 over 360. How many times does 240 go into 360? Well, I really don't know. I really don't know. I can't think mathematically, but I can eliminate those 2 n zeros and I got 24 over 36. Okay, I still don't know what that reduces down to, but I know they share a common factor. In other words, I know that 6 times 6 is 36, and I know that 6 times 2 is 12. Okay, so 240 into 360, I can divide out 6 from both of those things. If I divide out 6 from 24 into 36, I'm left with 4 on top and 6 on the bottom. So that would be 4 pi over 6. Well, I know that I can reduce that down because 4 and 6 share a common factor of 2. So 4 divided by 2 is 2. 6 divided by 2 is 3. So while that was a lot of verbal nonsense, that reduces down to 2 over 3 times pi. So we write that, the trig way to write it is 2 pi over 3. But that's the same thing as 120 times 2 over 360 times pi. It's the same thing. 2 pi over 3. 2/3 pi. That's what it means. 2/3 times pi. Let's do 135. This one appears to be more difficult because, you know, there's 3 digits and one of them's 3 and one of them's 5. But I'm a dummy, so I'm just going to do it the longhand way. 135 times 2. I have no idea, guys. I'm going to be honest with you. I don't know. Over 360 pi. Well, what's 135 times 2? I don't know. But 35, I know 35 times 2 is 70. And 100 times 2 is 200. So I got 100 times 2 plus 35 times 2. 135 times 2 is 270. Okay, so I got 270 over 360 times pi. 270 over 360 times pi. And how does that reduce down? How does that reduce down? Let me write it so we're not getting lost. 270 over 360 times pi. So let's reduce this fraction. See if we can't come up with one of these nice, clean, simple ratios. What are my common factors in 270 and 360? Well, think about 27 and 36. 6 is not one of them. But what other ways can we get to 36? 9 times 4? Does 9 go into 27? Yes, it does. 9 goes into 27 3 times. 9 goes into 36 4 times. So I've got 3 pi over 4. 3 times pi over 4. 3 pi over 4. Let's do 150. 150 times 2 over 360 times pi. Guys, it works for every angle. 150 times 2 is 300. So I got 300 over 360 times pi. Well, how many times does 300 go into 360? I don't know. You know, how can I reduce this fraction is the other way of saying it. What are the common factors between 30 and 36? Let's see, I got 5 times 6 equals 30, and 6 times 6 equals 36. So my common factor is 6. Pull those out, and I've got 5 pi over 6. Five pi over 6. Don't lose sight of the fact that 5 pi over 6 is the same thing as 300 pi over 360, or 150 times 2 over 360 times pi. It's all the same thing. Same, just simplified. This is a simplified fraction. The reason it's difficult is because when you see the unit circle given with these radian measurements, they all have different denominators. There's no common denominator, so it's not clear what you're looking at. And most students are like me, and they're reduced to just memorizing the radian measurements, trying to go, okay, pi over 6. I've seen students have all kinds of complex mnemonic devices to remember pi over 6, pi over 4, pi over 3. It's confusing because when you go, well, 6, 4, 3, okay, 2. But now what do you do for 2 pi over 3 and 3 pi over 4 and 5 pi over 6? There's no need to try to remember it. Just think about the degrees. Multiply times 2 over 360 times pi. That's, to me, the clean way of doing it. Well, now let's get over here to 180. Well, that seems like a significant line or a significant angle, but it really isn't. 180 times 2 over 360 times pi. Well, what's 180 times 2? It's 360. So 360 over 360 times pi. Well, ladies and gentlemen, that's 360 over 360 is 1. 1 times pi, that's just pi. So we'll just write pi here. So that's the radian measurement for 180 degrees. Okay, let's continue. 210. Looks hard. 210 times 2 over 360 times pi. Uh-oh, what do I do? Well, 210 times 2, that's 420. 420 over 360, I have no clue, ladies and gentlemen. I know it's an improper fraction, but Lord have mercy, I have no clue. But let's take 420 over 360 times pi. Let's see if we can reduce 420 over 360 times pi. Well, I have no idea, but let's try to reduce. What common factors are shared between 42 and 36? Well, 6 times 6 is 36. 7 times 6 is 42. So the reduced fraction is 7 pi over 6. That's the radian measure for 210 degrees. Let's do 225. 225 times 2, all over 360 times pi. What's 225 times 2? 450. 450 over 360 times pi. Let's give our intermediate 450 over 360 times pi. Well, how does that reduce down? I don't know. What are the common factors? Does 5 go into 5 goes into 45? 9 times 5 is 45, but 5 doesn't go into 360, so that isn't right. How else can I get to 45? Oh wait, how about the 9? I can divide a 9 out of there. Can I divide a 9 out of 36 or 360? I sure can. So 45 divided by 9, that leaves 5. Pi. 360 divided by 9, or 36 divided by 9 rather, leaves 4. So 5 pi over 4 is the radian measurement for 225 degrees. You don't have to remember it. There's no need to remember it. Let's take 240. 240 times 2 over 360 times pi. Well, what's 240 times 2? 480? 480 over 360 times pi. Let's reduce that down. What are the common factors between 480 and 360? Well, what are the common factors between 48 and 36? I know that 12 times 4 is 48, and I know that 12 times 3 is 36. So my common factor is 12. So let me pull a 12 out of the top and the bottom there. And I'm left with 4 pi, and then 12 went into 36 3 times, 4 pi over 3. That's the radian measurement for 240. Okay. Let's do 270. 270 times 2, all over 360, times pi. Oh, brother. Now what? Well, let's do this in two parts. 200 times 2 is 400. 70 times 2 is 140. 140 plus 200 is 340. So 270 times 2 equals, 200 plus 140. 200 times 2 is 400. 70 times 2 is 140. 400 plus 140 is 540. Oh, told you I was bad at math. 540 over 360 times pi. Let's write that out. 540 over 360 times pi. What are my common factors? We got 54, 540, and 36, 360. So 54 and 36. What are they? Well, 9 goes into 54. Does it? Yes, it goes into 54 6 times. 9 times 6 is 54. I had to think for a second there. 9 times 6 is 54, and 9 times 4 is 36. So let's write another. So wait a minute. What am I doing again? I'm pulling the 9 out. Is that what I'm doing? Leaving 6 pi over 3. Okay. 6 pi over 3. But can't that be reduced again? 6 divided by 3 is 2. Wait a minute. I'm doing something wrong. Oh, I was pulling a 12 out. Sorry, pardon me. Whoops. That's 6 pi over 4. Getting ahead of myself. 540 over 360, you pull out the 9, you get a 6 on top. You pull out the 9, you get a 4 on the bottom. So just in case that was unclear, I wrote 6 pi over 4, but I can still pull a 2 factor out of both of those. This becomes 3 pi over 2. Okay, so I'll write that here. 3 pi over 2. Sorry about that little error there. I don't want to confuse anybody. Just watch that part again. You'll see made a little mistake, but corrected it. 6 pi over 4 reduces to 3 pi over 2. 3 pi over 2 is the radian measurement for 270 degrees. No biggie. Let's continue. 300 times 2 over 360 pi. Well, that's 600 over 360 pi. What are my common factors? I got 60 and 36. 12 is a common factor. If I pull 12 out of 60, I got 5. If I pull 12 out of 36, I've got 3. So 5 pi over 3 is the reduction there. 5 pi over 3 is the radian measurement for 300 degrees. We're almost done. 315 times 2 all over 360 times pi. 315 times 2, that's 630 over 360. Well, I have no clue, so let me write it out. 630 over 360 times pi. Whoop. Okay. 63 over 36. What times what equals 63? 9 times 7 equals 63. What times what equals 36? 9 times 4 equals 36. So I got a common factor of 9. Let me pull those out. 63 divided by 9 is 7. 36 divided by 9 is 4. So 7 pi over 4. We don't need a calculator. This is 7 pi over 4. And that is the radian measurement for 315 degrees. Okay, 2 more and we're done. 330 times 2, 330 degrees times 2 over 360 times pi. Okay, so 330 times 2 is 660 over 360. So 660 over 360 times pi. 66 over 36. What are my common factors in 66 and 36? Well, whenever I see 66, I'm thinking 11, just like when I see 55, 66, 77. You can divide out 11. Well, what's left? 11 times what equals 660 or 66? 11 times 6. Well, okay, because 36 can't be divided by 11, but 36 can be divided by 6. So I've got 66 divided by 6, it leaves 11. And 36 divided by 6 leaves 6. So as crazy as this sounds, this is 11 pi over 6. Okay, 11 pi over 6. And you know what's nice is, that's the radian measurement for 330 degrees. You didn't really need to remember that. I didn't know it. I honestly didn't know it. I never did memorize that unit circle in my whole life. But you don't need to remember the unit circle anymore, do you? Because now you know. So now we're at the big final number, 360. 360 times 2 over 360 times pi. Well, 360 times 2, ladies and gentlemen, is 720. 720 over 360 times pi. That's my intermediate fraction. Let's reduce that down. 720 over 360 pi. Well, wait a minute. I just said 360 times 2 equals 720. So 720 divided by 360 is 2. So that forms a nice clean fraction because the denominator is actually one of the factors of the numerator. That means I'm going to come out with a whole number, and that whole number is 2. So my radian measure for 360 degrees is 2 pi. And that's how you remember it. So let me zoom out a little bit and show you all the cool work we've done. Using sacred geometry and no calculators, we computed all of the degrees. We found the degrees, remember, with the sacred geometry. And we were able to compute all of the radian measurements using a simple technique of degree times 2 over 360 times pi. Degree times 2 over 360 times pi. This could even be done for 1 degree. Let's try it. 1 degree, what would the radian measurement be for 1 degree? Just do it in your head. 1 degree times 2 over 360 times pi. Okay, so 1 times 2 is 2 over 360. How do I reduce that? Well, let's just divide the top by 2 and the bottom by 2. I've got 1 pi over 180. That is the radian measurement for 1 degree. Take another one. At random, 63 degrees. Okay, 63 times 2 is 126 over 360. Let me use a piece of scratch paper here. Okay, let's say we were going to do 63 degrees. What's the radian measurement? Well, 63 times 2 over 360 times pi. 63 times 2 is 126 over 360 times pi. Now, I don't have any clue. I promise I didn't think of this in advance. Let's just work on it together. 126, I can't like simplify this fraction very much. So let's just do let's do what we know we can do. Even if you think you can do something more complicated, just divide by 2. You know it's an even number, so you can divide by 2. What's 126 divided by 2? Okay, if we really had to, guys, if you really needed to go there, oops, I just drew a radical. It's been so long since I've done long division. If we needed to, we could do 126 divided by 2. 126 goes into 12 6 times, okay? And 126, or 2 goes into 6 3 times, so that's 63, okay? Obviously, we didn't need to do that, right? Because we did the 63 times 2. But here's I'm making a point. I'm illustrating a point. 126 divided by 2 is 63. 360 divided by 2 is 180. So I've got 63 pi over 180. Are we done? Well, that's accurate. That is the radian measurement for 63 degrees. But we've got more we can do. I guarantee it. There's more there. 63 is 9 times what? See, 9 times 6 is 54, 9 times 8 is 72, 9 times 7 is 63. Okay, and we know 9 goes into 18 2 times. So I can pull 9s out of the top and the bottom. And what I'm left with is I pull a 9 out of 63, and I'm left with 7. Okay, 7 pi. And I pull a 9 out of 180. What am I left with? 20. I'm left with 20. So my radian measurement for 63 degrees is 7 pi over 20. And to me, that's the real power of this degree times 2 over 360 times pi method. Because you're always going to come up with the right answer. And even if you feel like you can't simplify the fraction, or you just don't know, or you don't have a calculator handy, you can leave it in this form, and that's correct. It's just not simplified. Okay? So let's go back and just kind of marvel at our work for a minute. This is exciting. We'll overlay the watch to remind us that that cool harmony exists between the watch and the unit circle. So like a fun game to play is to say, what radian measurement is 2 o'clock? Pi over 6. What radian measurement is, how about 1030? 1030. Well, you lay it down here. 3 pi over 4 is 1030. How about 9 o'clock? Right on the dot, 9 o'clock. Radian measurement for 9 o'clock is pi, or that's 180 degrees. And we'll just do one more for fun. Let's get into quadrant 4. It always gets ignored. Poor guy's all by himself. How about 4:30? Seven pi over 4, 315 degrees. And then to kind of close off the festivities, 3 o'clock on the dot, is 2 pi for 0 degrees or 360 degrees. Ladies and gentlemen, brothers and sisters, comrades and friends, fellow countrymen, I hope this was helpful. And please be sure to celebrate Happy Pi Day, which is coming up. Show your teacher this circle can draw on using sacred geometry, and drop a old-fashioned watch on top of it and start talking about 45 times 2 pi over 360, and just watch the fascination and mystification come over the face of the teacher that you now know how to do this cool thing. Show your friends. Be a nerd. Be excited. Be part of the nerd core. Have a good day. Thank you.